Okay, so uh, let's unpack this. Imagine looking up at the night sky, and you ask that, well, that huge question, are we alone?
Right.
Or maybe, more scientifically, how many other advanced civilizations could be out there?
Yeah, and for decades, the go-to tool for that has been the Drake equation, right? It's this famous string of factors you multiply
To
together.
get n, that
Yeah.
magic number.
Exactly. And it breaks this massive mystery down. You've got star formation rates,
Why?
the fraction with planets, FP, how many are suitable for life, P,
Then life actually starting, FT.
getting intelligent, Phi, becoming advanced, FT, and the really big one, L, how long they last. Multiply them all up.
But, and this is where it gets really interesting, isn't it? Each of those letters, R, F, P, F, L, they aren't known numbers.
Oh, not even close. They're huge unknowns themselves.
Wow.
Riddled with uncertainty. I mean, how do you even start to, properly measure that uncertainty?
Beyond just throwing out best guesses. Yeah.
Exactly. And that's precisely what we're doing a deep dive on today. There's this fantastic paper came out of NASA research back in 1980.
By P.A. Sturrock. Uncertainty in estimates of the number of extraterrestrial civilizations.
That's the one.
So our mission today is to really get into how this paper tries to formalize all that uncertainty. Find out, which factors are the shakiest.
Where the biggest doubts lie.
Right. And explore some, well, pretty surprising directions it takes, especially when you start thinking about physics beyond what we know.
Yeah, it gets quite speculative, but in a structured way. What the paper points out right away is that the usual scientific approach, reporting a number plus or minus some standard deviation.
Like you see in lab results.
Precisely. It just doesn't cut it here. Not when you're dealing with factors like, say, the chance of life arising, or L, the lifetime. The uncertainty is just too wild.
Our ignorance is too deep for just a little air bar.
Exactly. So the paper argues you need to use full probability distribution functions for each factor, like mapping out the whole range of possibilities for R, for FP, for P, and assigning likelihoods across that range.
Gives a much more honest picture of what we don't know.
It does. And then it looks at how those uncertainties pile up when you multiply everything together. It uses a mathematical simplification, actually. Assumes the logarithms of the factors have a sort of standard Gaussian distribution.
Makes the math more tractable, I guess.
Yeah, it lets you see how the uncertainties combine. And looking at the estimates people were using back then, around 1980, you can see them in Table 1 of the paper.
Okay.
Even with what Sturrock considered pretty conservative uncertainty ranges for each factor, the final uncertainty in N is just enormous.
Okay, so what does that actually mean in numbers?
Yeah.
Based just on the spread in those estimates,
Yeah.
using this framework.
The paper calculates a 95% confidence range for N, get this, from about 10 squared, so 100,
Okay.
all the way up to 10 to the power of 10. That's 10 billion.
Wait, from 100 to 10 billion.
Yep. A factor of 100 million difference between the low end and the high end of what the model suggested was plausible then.
Wow. 100 million. That really drives home the scale of the uncertainty.
And the paper even says that's probably an underestimate because the input estimates back then likely weren't fully independent. People influenced each other's guesses.
Okay, so it's massively uncertain. But does the paper pinpoint why? Which factors are causing most of this huge spread?
It does, and this is really crucial. When you break down the variance where all that uncertainty comes from, one factor just completely dominates.
Which one? Let me guess. L.
You got it. L. The lifetime of an advanced technical civilization.
Dominates how much? Like, roughly?
The paper's analysis suggests L accounts for about 80% of the total variance in the final estimate of N.
80%.
Wow.
So 4/5 of our uncertainty about the number of civilizations boils down to just not knowing how long they typically survive.
That's basically it. And after L, the next biggest culprit, responsible for over half the remaining uncertainty, is
yes, yeah.
FAC, the fraction of planets that have intelligent life, where that life actually develops into an advanced, communicative civilization.
So how long they last, and whether they even make that final leap to being detectable or interstellar, those are the two real sticking points.
Absolutely. That's where our knowledge, or lack thereof, really hits a wall, according to this analysis.
Okay, so given that L, the lifetime, is this like 80% black hole of uncertainty, it makes sense the paper would dig into that more deeply.
It has to, right.
Yeah, and this is where it starts to get, well, pretty speculative, isn't it?
It does, yeah. But it's necessary speculation in a way. The paper argues that our estimate for L, how long a civilization might last, It isn't just a random guess. It's probably tied to some really fundamental assumptions we make.
Assumptions about how the universe works
Yeah,
and what advanced life might be capable of.
exactly. It boils it down to two really big, almost philosophical questions.
Okay, what are they?
First is what the paper calls hyperphysics, H, versus no hyperphysics.
Hyperphysics,
Yes.
like physics beyond Einstein.
Sort of. The idea is our current understanding of physics, relativity, quantum mechanics, is that basically it? Or do really advanced civilizations discover and use new laws of physics? A hyperphysics.
Something that might allow, say, faster than light travel or communication. Things like hyperspace and sci-fi.
Precisely those kinds of things. The paper notes this is really a philosophical stance, especially back then, because we had zero evidence for it. But the possibility is key.
Because it would totally change the game for how civilizations could interact or spread or even survive long term.
Absolutely. And the second big concept is linked to that. Galactic Federation G versus no Galactic Federation G.
So does an interstellar community exist? A galactic club where civilizations are actually in contact?
Right, and you can see the connection if hyperphysics H is real, allowing quick travel and communication.
Then a Federation G seems much more likely, maybe inevitable over cosmic time.
But if we're stuck with H, no hyperphysics, just the speed of light limit, then building a cohesive galactic federation seems incredibly difficult, maybe impossible.
Okay, so you've got these two big axes, hyperphysics, H or H,
Yeah.
and Federation, G O G. That creates four possible scenarios, right?
Yep. Four contexts a civilization could exist in. GH, federation with hyperphysics. Federation without hyperphysics, maybe slow contact. A GH, no federation, but they have hyperphysics, maybe isolated pockets. And GH, no federation, no hyperphysics, basically us, maybe.
And the paper tries to estimate the lifetime L differently for civilizations in each of those four boxes, and even assign probabilities to which box is most likely.
Exactly. It uses subjective probabilities, the author's own best guesses, basically for how likely each scenario is, and then estimates L within each one.
What's powerful there, I think, is how it explicitly links these huge unknowns about fundamental physics, about galactic sociology directly to L, the lifetime.
It provides a structure, a way to see how these big ideas cascade down into the Drake equation factors. It's a bookkeeping procedure, as the paper calls it.
Okay, so if L depends heavily on whether hyperphysics exists, and if there's a galactic federation, how does that flow through to the next question?
Mm-hmm.
How do we find them?
Right. How does it affect detectability?
Yeah. How do these scenarios change the odds of us spotting them, or maybe them contacting us?
That's the next logical step in the paper. It considers four main ways we might detect or be detected by an advanced civilization.
Okay, let's list them. There's intentional signaling, like radio beacons.
RB?
Yep. Then unintentional signals, radio leakage, RL, like our TV broadcasts escaping.
Then physical presence, manned surveillance, SM, so actual visitation.
And finally, automated probes doing radio surveillance, SR, listening posts sent out.
RB, RL, SM, SR. Got it.
And the key insight, following the previous logic, is that the likelihood of a civilization using any one of these methods probably depends on which of those four scenarios, GH, etc., they're in.
Makes sense. Like if you're in a galactic federation with hyperspace travel, why bother with slow, leaky radio beacons? Maybe you just show up or communicate instantly some other way. Or maybe you don't bother communicating with primitives at all.
Right. So the context dictates the likely method. The paper then takes its subjective probabilities for each scenario and the likelihood of each method within that scenario.
And crunches the numbers to estimate the expected number of civilizations employing each method, NRB, NRL, NSM, and NSR.
And this is where we see some really interesting relative numbers looking at Table 2 in the paper, specifically the final row with the logarithms.
Yeah, the results are quite striking. The log base 10 of NRB radio beacons is around 4.5.
Okay.
Log NRL radio leakage is about 5.5, so 10 times more numerous than beacons in this estimate.
Right. Then log NSM, manned surveillance.
That comes out around 6.5.
Whoa, so another factor of 10 higher than leakage?
In this calculation, yes. And then log NSR, radio surveillance probes, is back down around 4, similar to beacons, maybe slightly less.
Okay, let's just unpack the significance of that. If we take these numbers, calculated using the paper's framework and the author's admittedly subjective inputs,
A big if, but let's run with it.
it suggests that the most numerous type of potentially detectable civilization activity might be manned surveillance and SM, physical presence.
That's the implication of these numbers, yes. It's a pretty provocative result. It suggests that Based on this line of reasoning, encountering ET might be more likely via physical observation than via radio signals.
Followed by radio leakage, which is still significant.
Yep, NRL is next.
And then intentional radio beacons, NRB, and automated radio surveillance probes, NSR, are calculated to be considerably less numerous.
Roughly similar to each other, but yeah, significantly less than SM and RL in this specific model.
It's really important to stress, as you said, this isn't presented as the definitive answer.
No, not at all. The paper frames it as a tool, that bookkeeping procedure, to make all the assumptions explicit. You can plug in your own probabilities for hyperphysics or Federation likelihood and see how the results change.
But it definitely highlights how crucial that fundamental question about hyperphysics really is. It seems to drive so much of this.
It really does. The paper argues it's probably the single most important fork in the road for these kinds of estimates. And it's a fork based still largely on philosophical outlook or scientific judgment, not hard data.
Which leads back to that striking result about man's surveillance potentially being the most numerous. If NSM is high, what does that imply, according to the paper?
Well, if manned surveillance across interstellar distances is actually common.
It pretty much demands something like hyperspacecraft, right?
Exactly. It strongly implies that hyperphysics H must be real. You can't have widespread interstellar manned surveillance easily without it.
So the high NSM result is directly tied to scenarios where H is likely.
Correct. And this ties into the whole Fermi Paradox discussion. If they're out there, where is everybody?
The great silence.
Right. The paper acknowledges one answer, argued forcefully by people like Michael Hart around that time. Maybe the silence means we really are alone or effectively alone.
But the paper's own calculations, especially that high NSM, point towards another possibility, don't they?
They do. What if surveillance is happening, but it's deliberately covert?
Like terrestrial intelligence gathering, you don't announce you're spying.
Precisely. So the fact we haven't seen obvious visitors or detected overt signals might not mean absence.
It might mean they're using methods enabled by that very same hyperphysics methods like stealthy interstellar travel that make their surveillance incredibly hard, maybe impossible, for us to detect right now.
It shifts the potential explanation for the silence from "they're not here" to "they're here, but undetectable by our current means or understanding."
So this whole deep dive into a paper from over 40 years ago now, it's a really potent reminder, isn't it, that this question of ET isn't just about pointing telescopes.
Not at all. It's deeply tangled up with these huge uncertainties: how long societies last, whether our physics is the ultimate physics.
What galactic society might even look like if it exists.
And the framework, even with its subjective inputs, is valuable because it shows how different answers to those big questions radically change what we should expect to find and how.
It really highlights that our strong focus on SETI, on radio searches, while totally logical given our tech.
It implicitly bets on the no hyperphysics scenario being true, doesn't it?
Yeah, it kind of does. So, okay, here's a provocative thought to leave you, our listener, with, based on Sturrock's 1980 logic.
Go for it.
Does this calculation suggesting manned surveillance might actually be the most numerous contact modality out there? Does it fundamentally challenge the core assumptions driving our current search strategies?
And building on that, if contact hasn't been obvious, if the universe seems silent, is the simplest explanation that we're alone? Or could it be that the universe operates on principles, like hyperphysics, that we don't grasp yet?
Leading to methods of contact or non-contact, like maybe widespread covert surveillance, that are just completely outside our current ability to detect or even conceive of.
Something to definitely mull over next time you find yourself looking up at the night sky.